Hello and welcome to this video about proofs in linear algebra. In this video we'll investigate the fourth linear transformations theorem. So this theorem says these three things. The first thing is that the function or linear transformation L is one-to-one if and only if its kernel only contains the zero vector. One-to-one means that we can create an inverse function for it in the range of this function, but not for the whole codomain. So it isn't really invertible. I've written if with two F's. This isn't a typo. It's short for if and only if. It works like a double implication arrow. Onto means that the output of the function covers the whole codomain. So let's prove the first part of this theorem. We'll prove it true in the forwards direction first. We'll assume that L is one-to-one, and we want to show that this implies that the kernel will only contain the zero vector. We'll get any vector in the kernel, which can stand for every vector in the kernel, and call it x. And applying L to it gives us the zero vector, because it's the main property of the kernel. In fact, that's its definition. And then we'll use this past theorem to say that applying L to the zero vector gives us the zero vector. So now we can write it out like this. I didn't really have to write it, because it's already written above it, but I wanted to highlight this result. Then we can use the property of one-to-one functions to get this result, that x is equal to the zero vector. And this means that only the zero vector can be in the kernel, so we've proven part A in the forwards direction. So now we have to prove part A in the reverse direction. We'll start with the kernel only containing the zero vector and show that L must be one-to-one. So we'll take any two vectors from the domain of L, which is V, and we'll assume that this equation is true. We have to deduce that these two vectors x and y are equal from this equation. We can subtract Ly from both sides. We can use theorem 3.1 much more freely now, and just subtract these vectors as though they were numbers. We don't need to invoke all of the vector space axioms and theorems like we did earlier. We'll use the properties of linear transformations to gather everything into the brackets of one L function. Now we can say that this vector is in the kernel of L. And because the kernel only contains the zero vector, then we can immediately say that this vector is equal to the zero vector. So then we can add y to both sides to get this equality that we were trying to get earlier. And this is enough to show that L is one-to-one. We've proven part A in both directions, so now we've proven part A. We'll use a light-coloured box to show that we've proven part of this theorem, but not the whole theorem. So now to prove part B of this theorem, we've studied what the dimension of a vector space is in earlier proofs. We'll start to prove this in the forwards direction. Now if L is one-to-one, then this implies that the kernel only contains the zero vector from part A of this proof. So the dimension of the kernel is zero, because it doesn't contain any non-zero vectors. And now to use this equation that we've proven before in a past theorem. We'll substitute the value of the dimension of the kernel into this equation, which is 0. And simplifying this equation gives us this equation, which is what we're trying to prove. So we've proven part B in the forwards direction. So now to prove part B in the reverse direction, we'll start with this formula. And using a past theorem, we can say that this quantity is 0. We've already done all of the calculations for this when we've proven the forwards direction of this part. And this implies that the kernel only contains the zero vector. And we can invoke part A of this theorem to say that L is one-to-one. So that's it. We've proven part B. And now to prove part C. This was left as an exercise for the reader, maybe because the proof didn't fit in the textbook. So I've tried my best to work something out. We'll do the forwards direction first, which is really easy. The definition of onto is that the image of a function must be equal to its codomain, so we'll write this down straight away. And so obviously the dimensions of these vector spaces must be equal, so the forwards direction has been proven. Now to do the reverse direction, which I found a bit tricky. I did a bit of improvisation, so I hope you like it. Firstly, I'll set the dimensions of these two vector spaces to n. And codomains are usually the field used by the vector space raised to the power of an integer. In this case, it's reals raised to the power of n. We could substitute rational or complex number sets in here as well. And so the image of L is a subset of W and has the same dimension as W, so it has to be Rn, because it's the only possible n-dimensional space that can fit inside Rn. And so because both of these spaces are equal to Rn, then they must be equal to each other, so this completes the whole proof. The last part of this proof looks a bit dodgy, but it might be good enough to inspire someone to do it properly. So I hope that you found this video to be helpful and educational. Please click like and subscribe if you did. Please feel free to write anything helpful in the comments and to share this video. And thanks a lot for watching.